Based at Southampton University, Wolfson Electrostatics has specialised in the hazards and applications of static electricity since 1971. They provide consultancy, R&D and testing services to many industries worldwide, from avionics to viscose production. In the petrochemical sector, Wolfson advises on hazards associated with fuel handling and storage. Here, one of the biggest issues is reliable earthing of conductive objects in flammable atmospheres, often difficult to achieve in an industrial operation.
Most people consider static electricity to be associated with insulators such as plastics. But from the point of view of fire and explosion hazards, it is insulated conductive objects which are the more dangerous when they become unearthed. In virtually all incidents of fire and explosions caused by static electricity and investigated by Wolfson, the source of ignition was provided by an insulated conductor, not a plastic surface. This is why combining conductors and insulating materials together in the same product gives cause for concern in situations where static may be generated. Why is this? Well, the answer is quite simple. The presence of electrostatic charge on a surface is in itself not hazardous. It is the electrostatic discharge, for example in the form of a spark, which can ignite the fuel and may cause electric shocks.
The difference between the electrostatic discharge, or ESD, of an insulating or non-conductive material, such as plastic, and an insulated conductive material is shown here, using two lengths of polyethylene pipe designed for the transfer of fuel underground. One is manufactured completely from plastic. The other also from plastic, but with an inner conductive lining. We can apply an electrostatic charge by rubbing the outer surface, and then promote a discharge to a probe connected to an oscilloscope. The oscilloscope measures the intensity of the ESD. Under extreme conditions of charging, which are never met in the fuel retail environment, so-called brush discharge from plastics can cause ignition. But there's a big difference between electrostatic discharges from plastics and those from unearthed conductors. Even when charged at 15,000 volts, the non-conductive plastic pipe gives no discernible electrostatic discharge. Here's the demonstration again, this time using the pipe with the inner conductive layer. This time, the pipe gives an energetic spark, which appears as a sharp spike. The magnitude of this spike determines the incenditivity of the ESD. That is, its ability to create a spark that could ignite a flammable material. This shows itself as an electric shock when handled. For the purpose of direct comparison between the two types of pipe, instead of rubbing the surface, the applied electrostatic charge can be provided in a more controlled way, using the same conditions for both samples. In this case, a corona source is used at 10 kilovolts and applied in an identical way to the outside surface of the two pipes. Again, there's no electrostatic discharge observed with the non-conductive pipe. However, in the conductive line sample, the ungrounded conductive layer produces a spark discharge. Similarly, charging the inside surface of a non-conductive pipe to 10 kilovolts produces no electrostatic discharge. Once more, with the conductive line sample, the ungrounded conductive layer produces a spark discharge. The laboratory test has demonstrated how easy it is to create an electrostatic charge in a short length of pipe, and the difference in electrostatic discharge in a non-conductive pipe and a pipe with an inner conductive layer. So, what does this mean in terms of fire or explosion hazard? To create a spark, sufficient ESD energy needs to be generated within the ignition zone. The minimum ignition energy, or MIE, of a fuel is defined as the spark energy required to ignite fuel vapor in its most flammable concentration. The MIE is the lowest point of the ignition zone in the graph. Petrol vapor in air has an MIE of around 0.25 millijoules. With biofuels, the MIE can be even lower, at 0.14 millijoules. The electrostatic discharge of non-conductive pipe can't ignite flammable vapors because there's insufficient energy to cause ignition. Plastic surfaces can only store small amounts of electrical energy as they have a small effective capacitance. But laboratory measurements have shown that there's enough capacity in a 1 meter length of conductive lined pipe to have spark energy in excess of 25 millijoules, over 100 times the MIE of petrol vapor and nearly 170 times that of biofuel vapor. This laboratory demonstration clearly shows the ESD from conductive pipe creating a spark that ignites fuel vapor. Since there are no conductors in the non-conductive pipe, it's impossible to get sparks under normal fuel flow conditions. Brush discharges from plastics are theoretically possible, but repeated tests on the non-conductive pipe under normal fuel flow conditions have never shown them to contain sufficient energy to be hazardous. When connecting two conductor elements together, it's good practice to apply force between the surfaces to reduce contact resistance. The conductive inserts used to bridge the surfaces of the conductive lined pipe are pushed into place without any device to ensure permanent contact, thus increasing the chances of a break in conductivity. The inner bore of all extruded polyethylene pipe varies due to manufacturing tolerances, and thus the conductive pipe inserts can be too loose or too tight, again leading to the possibility of a break in conductivity. The inserts are also directly exposed to the fuel flow, so that an insulating film, such as those found in many fuels, could penetrate the contact during fuel flow. Breaches of the electrical connection to earth may create an insulated conductive section with consequent high risk of spark discharge.
What we've shown in these tests that we have done is that you can obtain spark discharges from sections of conductive lined pipe, assuming they become ungrounded or unearthed, but you can't generate spark discharges from non-conductive pipe. The conductive lined pipe system we've shown can produce electrostatic spark discharges. These spark discharges are very energetic. They can be generated simply by handling sections of pipe, and they can also be generated by fuel flow through the pipe. The non-conductive pipe system doesn't contain conductive sections and therefore is incapable of producing spark discharges under any conditions. The conductive part of conductive line pipe can acquire charge due to simple handling. This can produce sparks which give the operators and installers an electric shock. I think it's very difficult to ensure that the sections of conductive line pipe are grounded during installation. It would be very difficult and practically impossible to ensure that it's grounded at all times. Any system that contains conductive elements, and that includes conductive lined pipe systems, should be regularly checked to make sure that all components are safely grounded, and this should be done routinely throughout its lifetime.
So, in summary, we can say that conductive pipe can generate sparks if unearthed, may and does create a risk of electric shock to installers, produces a risk of spark ignition during handling, and a risk of spark ignition in use if unearthed, and must be earthed at all times. It's recommended that earthing of conductive pipe is checked regularly. None of these points applies to non-conductive pipe.